Okay, I want to start this video with a motivating problem, which actually is not exactly the doubling time problem. It actually comes from the doubling time problem. So, but to get to the motivating problem, we have to describe the doubling time problem first. So, suppose you deposit an amount p sub 0 into some savings account that yields an annual interest rate of r. This means that the amount of money you will have in that account after t years is p of t equals p sub 0 times 1 plus r quantity to the t. Let's take that as for granted. That's actually sort of the definition of what an annual interest rate is. So the question is, how long will it take to double your initial investment? All right, so the answer is, at the time t, when your investment will have doubled, so at the time t, some t years in the future, we will have, well, that p of t equals 2 times p sub 0. So 2 p sub 0 is equal to p sub 0 times 1 plus r to the quantity t. So dividing both sides by p sub 0, we have 1 plus r quantity to the t is equal to 2. And so solving for t by taking the natural log of both sides, we get the natural log of quantity 1 plus r to the t is equal to the natural log of 2, and so the rules of natural logs mean that you can take that exponent t down, so we get t times the natural log of 1 plus r is equal to the natural log of 2, and now dividing both sides by the natural log of 1 plus r, we get that t is equal to the natural log of 2 over the natural log of 1 plus r. So it will take the natural log of 2 over the natural log of 1 plus r years for your investment to double. Okay, great. So far, just pre-calculus. However, just to give things a name, let d of r be the doubling time for an account with an annual interest rate of r. The previous solution is correct, but that formula, d of r is equal to the natural log of 2 over the natural log of 1 plus r, is not particularly memorable. And more problematically, it's not particularly useful for calculations in your head. If you imagine, if you're an investment advisor, having to sit there and calculate the natural log of 2 over the natural log of 1 plus r while you're trying to sell somebody on some sort of investment plan, not particularly useful. And so in practice, what people use is what's called the rule of 72, which says that a savings account with an annual interest rate of r%, now remember, this r is not exactly the same r as we had over here. This is 100 times what we had over here because it's percents. That a savings account with an annual interest rate of r% takes approximately 72 divided by r years to double. Okay. So the question is, and here's our motivating problem, where does that 72 divided by r come from? It doesn't look a whole lot like the natural log of 2 over the natural log of 1 plus r, but still it seems to work, as we'll see by the end of this video. So, okay, hi, this is Tim Shu from San Jose State University, and I'm here today to talk about linear approximations and differentials. So we've already seen the motivating problem of doubling time, and motivated by trying to solve that problem of finding a good approximation for doubling time, I'll talk about the linear approximation to a function f of x near x of a. We'll do a particular example of the natural log function. We'll talk briefly about some other terminology for linear approximations, and finally we'll get back to, in the end, justifying the rule of 72. Okay, so as a review, let's start by reviewing the tangent line to y equals f of x at x equals a. So recall, by which I mean, if you don't remember this, go back and review it really quickly. The slope of the tangent line to a function y equals f of x at x equals a is f prime of a. Remember, that's one of the fundamental interpretations of the derivative. Furthermore, the tangent line to y equals f of x at x equals a passes through the point a comma f of a. And so from the point slope formula, because we have a point through which the tangent line passes, and we have the slope of the tangent line, we know, so since the tangent line passes through a comma f of a and has slope f prime of a, the equation of the tangent line is y minus f of a is equal to f prime of a times x minus a. Or in other words, moving this f of a over to the other side, y is equal to f of a plus f prime of a times x minus a. So there, that's the equation of the tangent line. Remember, these red terms, f of a, f prime of a, and a, those are all constant terms. And so that really is the equation of a line. So the only variables here are y and x. All right, so here's a review again. Here's the equation of the tangent line to f of x at x equals a. So because the tangent line to y equals f of x at x equals a is close to the actual graph y equals f of x at x equals a, and here's a reminder of what that is. So here in red is the actual graph y equals f of x, and there in blue is the tangent line. As you can see, close to x equals a, at the point at which the tangent line is calculated, the tangent line is very close to the actual graph, and so their y values are very close, which means that the y value of the actual curve, f of x, is approximately equal to the y value of the tangent line, f of a plus f prime of a times x minus a. So this approximate equation is called the linear approximation of y equals f of x at x equals a. And there it is again. So note that if f happens to be concave up at x equals a, if it's a smiley face, then this linear approximation at x equals a is an underestimate. And what do I mean by that? Well, here's an example where indeed f of x is concave up at x equals a over here. And we can see that the linear approximation at x equals a is an underestimate because, well, there it is. Oh, there it is up there. You point at the picture and you see that the tangent line is underneath the actual curve because f is concave up at x equals a, and so the tangent line approximation, the linear approximation, is an underestimate. And similarly, if f, as we'll see actually from an example in a minute, if f is concave down at x equals a, then the linear approximation at x equals a is an overestimate. So here's an example, the natural log function. So let's find the linear approximation of f of x equals the natural log of 1 plus x. That should look familiar from the doubling time problem at x equals 0. So let's calculate. So f of 0, here's the not so hard part. If you plug in x equals 0, you get the natural log of 1 plus 0, which is the natural log of 1, which is 0. So we need to find the value at 0, and then we need to find the value of the derivative of f at 0. So that's next. Well, first we have to find the derivative of f. F prime of x is equal to 1 over 1 plus x. Remember, there's actually a little invisible chain rule term here, which just happens to be 1, so we can ignore it. Anyway, f prime of x equals 1 over 1 plus x. And so plugging in 0, f prime of 0 is equal to 1 over 1 plus 0 is equal to 1. And so the linear approximation to the natural log of 1 plus x at x equals 0 is f of x is approximately equal to f of 0 plus f prime of 0 times x minus 0. And so remember, when you take this linear approximation, one of the things that the mechanical things that people get wrong on this subject is that they forget to plug in the actual value at where you're taking the approximation. You have to plug in that value to get something sensible out here. Anyway, after plugging in that value, so you put in 0 for f of 0 and 1 for f prime of 0, and this minus 0 goes away. And so we see that for x, values of x near 0, f of x is approximately equal to 0 plus 1 times x minus 0, or in other words, f of x is approximately equal to x. That is, so again, when we have a value of x that's close to 0, then the natural log of 1 plus x is going to be pretty close to the value of x. Anyway, so we just saw that the linear approximation f of x equals the natural log of 1 plus x at x equals 0 is the linear function y equals x. And so in a graph, you see here in red is the actual function f of x, the natural log of 1 plus x. And here's the graph of its tangent line, and we can see that for x close to 0, this is a pretty good approximation, and for x farther away from 0, it's a less good approximation. Actually, if you want just to see how things change when you sort of look closer and closer to 0, well, here's the same graph again, except only going from minus 0.5 to 0.5 instead of minus 1 to 1, and you can see that we get a better approximation. And if we zoom in even more, so x is between minus 0.1 and 0.1, and y is between minus 0.1 and 0.1, we see that it's really a very, very good approximation. It's sort of, even percentage-wise, it's really, really very good. So we see, as you get closer to the point in question, as you get closer and closer to here taking the approximation as 0, you get a better and better approximation. And in fact, that's actually one definition of the existence of the derivative, that as you zoom in closer, you get a better approximation. Oh, sorry to get all deep on you there, but it's true. The more you actually use some piece of math, the deeper the stuff that the thinking you tend to need. Okay, coming back down to earth a little bit, let's talk about some other terminology for linear approximations. One term alternate terminology for linear approximations is the term local linearization. So remember, again, here's the linear approximation of the function y equals f of x at x equals a. That's f of x is approximately equal to f of a plus f prime of a times x minus a. Now, it's convenient to have a name for this whole right-hand side, what that approximation is, and so we define capital L of x to be f of a plus f prime of a equals x minus a. That's really just the right-hand side of the linear approximation, and so we naturally call that the local linearization, or simply the linearization of f at x equals a. Another alternate terminology for linear approximations is differentials. So again, here's the linear approximation of y equals f of x at x equals a there, and there's the linearization, which is just a name for the right-hand side of the linear approximation. So another notation for L of x uses differentials, which we can define as follows. We define dy to be equal to L of x minus f of a, and this is sort of the trickier one. So dy actually represents the change in the approximation, not the change in the actual value of f of x. That would be delta y. dy actually represents the change in the approximation, so that's L of x minus f of a. So put that over here. That's the change in the approximation. And so if we define dx to be, which is really the same as delta x, to be x minus a, then we see that this equation here, putting f of a over on the other side, becomes precisely dy equals f prime of a dx. There it is. And if we consider that same linearization not only at a single point x equals a, but at an arbitrary x, we can also write dy equals f prime of x dx. And yes, that notation is occasionally useful. Actually, you'll see it in various other circumstances. But you know, that's the idea, that this sort of represents the change, that the derivative represents the change in linear approximation. Okay, so circling back to our original problem, the rule of 72. What justifies the rule of 72? So remember, as we sort of found out at the beginning, that the exact value of the doubling time d of r of some account as a function of that annual interest rate r is precisely d of r equals the natural log of 2 over the natural log of 1 plus r. And remember, our motivating problem was to find some sort of reasonable approximation of this right-hand side. So if you recall, the linear approximation to the natural log of 1 plus x at x equals 0 is precisely that the natural log of 1 plus x is approximately x. So this stuff on the bottom here is approximately r, and we see that approximately d of r is approximately equal to the natural log of 2 over r. And if you sort of figure out the value of the natural log of 2, it's 0.69 blah, 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 blah. So d of r is approximately 0.69 blah, blah, blah over r. So again, the linear approximation to the natural log gives approximate doubling time. D of r is approximately 0.69 blah, blah, blah over r. But since 72 has a lot more small integer divisors than 69 does, we sort of further approximate this by the rule of 72 that says that a savings account with an annual interest rate of r% takes approximately 72 over r years to double. And remember, it's 72 over r instead of 0.72 because this is r%, and so this is 100 times the actual interest rate. Just as a point of practicality, if you were actually doing this in your head, it's a little bit of a pain to try to divide 72 by 7. So if r% is equal to 5%, 7%, or 10%, we sometimes want to use the rule of 70. You know, it's all an approximation anyway. Okay, so how good an approximation is this? So remember, if d of r represents the doubling time for an account with annual interest rate r, so if r is 1%, the actual doubling time is 69.66 years roughly, and the rule of 72 gives you 72 years, 2%, 35 versus 36, and so on, 23.45 versus 24, 17.67 versus 18, 14.21 versus 14. Oh yeah, I should say there's these percentage rates with asterisks, 5%, 7%, and 10%. Those I all use the rule of 70 instead of the rule of 72 because it's much easier to divide 70 by 7 than 72 by 7. Anyway, so you get these approximations here, and you see they're pretty good. And for 7, 8, 9%, they're very, very good. So here's a thought question. You may notice actually that the strange thing is, even though the actual numerator for that fraction was 69 plus some other stuff, even though that's the case, and 72 is farther away from 69, we seem to actually get, if you look what happens down here as r increases, we actually seem to get a better approximation with 72, which is farther away from 0.69, or from 69, than we do with 70. And so it must actually be the case that using 72 instead of 69 somehow cancels out the error in the linear approximation. So there's one error that you get from taking linear approximation, and there's another error that you get by approximating 69 with 72. And I leave it to you to think about, and that over-underestimate stuff is actually sort of the key point to think about there, why it is that using these two errors actually somehow cancel each other out. All right, that's enough for now. Go try some problems. As a warning, by the way, that I don't often give, real problems on this subject. These are so linear approximations are so useful that you can actually use them to solve real problems. But the real problems, if your instructor is so bold as to assign you some, they're kind of long and they're all different. They're not the sort of thing where you can sort of use a cookie cutter method to do every single problem the same way. So with that warning, go do something useful. Thanks very much. Bye.